yada, an minus 1b is n. This is Kalman controllability condition, right? So you can recover Kalman controllability condition. Okay? But look at this here. So we said the log, if the log is satisfied, what do we get?
Accessibility.
Accessibility, very good. So we don't get controllability. So this guy actually implies this, okay, this is common controllability condition from linear algebra. They conclude controllability. Here we conclude accessibility. Right? Not quite there. So get a couple of examples to show how this is a useful computational tool, and I don't need to go and compute the reachable set every time. I just do Lie brackets, which is very easy to compute. But you're saying you're only concluding accessibility and not controllability. So why not controllability? Why log implies accessibility only, not controllability? Right? What can go wrong? So let's recall our example here that we just played with. X dot equals u, y dot equals x squared. We know that the reachable set was biased. This is your origin. What happened in terms of Lie brackets? Let's see. So we covered the Lie infinity. It was actually just Lie 2. We did two order Lie brackets. The first vector field was this guy, and the second was this guy. This was g of 0, and this one was fg with g, second order, of 0. Okay? So if I look at this structure and I'm trying to see, okay, we're concluding accessibility. Why we're not concluding controllability? What was the main difference between accessibility and controllability? If you look here, what's the main difference? We have bias and directionality, right? We can move forward in some direction, not the reverse. Which, in other words, if you can reverse the flow along all of your useful vector fields, you can conclude controllability, right? So can we reverse the flow along G? Can we reverse the flow along G? Any suggestion? This is our system. This is F. This is G. Can we reverse the flow along G? Come on, guys. Can we reverse the flow along G or not? Yeah, just make your input negative. That's it. So you can reverse the flow along G. Okay. So this allows you to move along the x-axis. What about the y-axis? Can you reverse the flow along the vector that is providing motion along the y-axis? Can we? Why? Why not? Because if you look here, if this is like UG and UG, so you get Lie brackets, the linear operation, so you get U squared outside. This is not always the case, by the way, but this is a good analogy, okay? So no matter how you change your U here, you get nothing. I mean, you get no reverse, okay? So this is a biased thing. This is a biased vector field. So this system is not controllable, it's only accessible. The log implies accessibility, and to go from accessibility to controllability, I need to check if all my vector fields, if they can be reversed or not. This guy can, this guy cannot. I know this from the system structure already, because here, look at this system, it's super simple. I can use my intuition, and I mean, it's super clear. Well, x is free, but y dot is always positive, so I cannot decrease y. Okay? So if I replace this by x cubed, what do you expect? If this is x dot equals u and y dot equals x cubed, what do you expect? Come on, guys. I mean, you don't have, I mean, this is an engineering class. You should have intuition. What do you expect? X cubed. There's no trick here. What do you expect about x cubed?
Multi-modal control.
Yeah, because you can manipulate x to be positive and negative and get the y that is required. And if you think about it in terms of Lie brackets, then here, what did you get when you have x squared? The first order Lie bracket, f and g vanishes because the one derivative of x squared is 2x evaluated at the origin vanishes. Now if it's x cubed, the Lie bracket will vanish, the second order Lie bracket will vanish, and the third will give you the motion. So the third will have f, g, g, and another g. So 3 g's, it's odd, it's not even, okay? And my message here, yeah, so actually Kautsky, 1990, he proved that x dot equals u, y dot equals x to the m is a small time locally controllable from the origin if and only if m is, yeah, okay? But what I'm trying to say actually is that don't rely on your intuition always, okay? So I'll give you an example. U, y dot equals x, z dot equals x times y. If you think about this system, well, x is free, I can manipulate it, then by manipulating x, I can manipulate y, positive and negative, and it seems that if I can manipulate x and y, I can manipulate z.
No, z is always positive, z dot.
Why?
Because if u is positive, x is increasing, and if x is...
Did you see what you just said? X is increasing. You didn't say if it's positive or negative.
Yeah.
Okay? So let's see. But I mean, it's along these lines. You're almost there. Let's see. So this is here is my f. It's 0x and xy. Here is my g, which is multiplying u, 1, 0, 0, right? So let's compute our Lie brackets. I have f of 0 vanishes. G of 0 is 1, 0, 0. Very good. So this is one thing. What else? Let's compute f and g. So this you get, if you look at just by here, you get 0, negative 1, and negative y. And if you evaluate it at the origin, you get 0, negative 1, and 0. So actually, let me show you this for your sake. So I'll just show you that how useful this thing is. So since x, y, and z, and I can define my coordinates as x, y, and z, right? My f was 0, x, and x times y, I guess, right? My g was 1, 0, 0, right? And I made this function, which is just a couple of lines here, that takes two vectors and the names of the coordinates and gives you Lie bracket. So Lie bracket q, f, and g, it will give you this 0, negative 1, and negative y that I just wrote. And you can keep doing that. So this is v, the first order Lie bracket. I can do the same now. Change this to v. So v with what is coming completely vanishes, and g, it also completely vanishes, okay? So you're welcome to build a similar function and play with it for all your homework examples. So here, when I do this with f or g, I got 0 vectors, so completely vanishes. So I'm done, I mean, no more differentiation, so I got the Lie infinity of f at the origin. What is that? This is the span of 1, 0, 0, the g, and this guy, which is 0, negative 1, and 0. This is what? This is R2. So what do you conclude about your system here? What do you conclude? What? accessible. Very good. So the lark is not satisfied because this is strictly less than the T0 R3, which is R3, right? So the lark is not satisfied, and the lark, remember, the lark is necessary and sufficient. Okay, so if it's not satisfied, it's not accessible for an analytic system. This is an analytic system. So by the lark condition, this is not accessible. What do you mean by not accessible? What do you mean by not accessible? What do you know about the reachable set? It's not accessible. What do you know about the reachable set?
No interior points?
Say it again?
It has no interior
No interior points. Very good. So what does this imply? What do you think about the reachable set? If it doesn't have any interior point, what does it imply? Any idea?
Your
Projection.
trajectory is prescribed always, that you cannot move freely.
Yeah, very good. It's very close. That your reachable set is not open. It doesn't have enough points. It's just a slice. It doesn't have an interior point, right? It's just a slice. And actually, yes, we can even characterize that even more. Why? Because I can form here a distribution delta that is the span of my f, which is, what was the f? So 0 xy, this is f,